we had ended the last video with this pseudo notation integral over gamma f1 dx1 plus dot 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 fn dxn. And our goal was to make this notation precise. Now let's think about what is happening in this notation by tying up this vector field to the most common vector field studied in mathematics and physics, that is the gradient of a differentiable function where f from u to r is C1 smooth. So if you start with a C1 smooth function on the open set U, then the gradient is going to give you a natural vector field. Not only that, we know what the gradient vector field is going to be. It's going to be del f by del x1 comma dot 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 del f by del xn. This is just basic way back when we studied differentiation of functions defined on open sets in R, and we had seen that this is nothing but the gradient of f, right? So the gradient of f gives a natural vector field. Now there is a common notation for the gradient or the derivative map in this situation. It's called the total derivative, and that sort of suggests what is happening. We define this another pseudo notation df of a to be del f by del x1 dx1 plus dot 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 del f by del xn dxn. And this object is often called the total derivative. Okay, so this intuitively captures the fact that the net change in the function f at the point A is nothing but the change in the direction x1 multiplied by an infinitesimal change in x1 plus dot 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 change in xn multiplied by an infinitesimal change in the direction xn. So this sort of physical intuition motivates this definition, but it mathematically makes no sense. Okay, but we can try to make sense of it by plugging in a vector v. Let's say you want to find out what dfav is. Okay, so again, since I am confusing between small f and capital F, let me just stick to this f from u to r. U is subset of Rn. So don't get confused because there is a capital F vector field also. So dfav, we already know that this is nothing but del f by del x1 v1 plus dot 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 del f by del xn vn, where v is v1 to vn, right? But you can get v1 to vn by taking the image of v under the dual vectors. So let e1 dot 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 en be the standard basis, and let e1 star comma dot 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 en star be the dual basis. Recall that this means that ei star of ej is the Kronecker delta delta ij, which is 0 if I is not equal to j and 1 if I equal to j. Okay, so these standard dual vectors e1 star to en star, when you plug in v, ei star of v is nothing but the ith coordinate vi. Okay, this is all elementary linear algebra. So dfav, I can also write it as del f by del x1 at a e1 star of v plus dot 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 del f by del xn at a en star of v. Okay, so by using these dual vectors, a basic concept from basic linear algebra, we are able to write down the formula for the derivative map via these dual vectors. But wait a second, this looks too similar to this total derivative thing. So define dxi to be nothing but ei star. Then that pseudo notation becomes precise. pseudo notation df becomes precise, and indeed under this notation dfa is a map from Rn to R. You can plug in a vector, and you will get out a number. So everything has been tied together now. The total derivative that you saw in multivariable calculus is nothing but our DFA in disguise. The moment you define the dxi's or as ei star, everything starts to make sense. Okay, so let's make a summary of this discussion with the following definition. We denote by dx1 to dxn the dual vectors in Rn of the standard basis. In other words, dxi from Rn to R is a linear functional with the property that dxi of ej is delta ij. Okay, now given a function, differentiable function, of course, given a differentiable function f from u to R, u subset of Rn is open, we define the functional df from Rn to R by del f by del x1 at a dx1 plus dot 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 del f by del xn at a dxn. So this functional is at a. Okay. In fact, let me be a bit more precise. We define this functional. We define the map. That's the best way to say it. We define the map df. This is from u to Rn star by df at a acting on v is nothing but del f by del x1 a dx1 v plus dot 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 del f by del xn a dxn v. So essentially what this df does is that for each point a in u, it outputs a linear functional, and the linear functional is essentially nothing but the derivative map of f at the point a. Okay, so for each point a in u, you get a linear functional from Rn to R. Okay, the next definition is going to be one of the central definitions of this course, definition of differential 0 and 1 forms. So the definition is as follows: let u subset of Rn be open. A 0 form on u is by definition a function. F from u to R is a function. We say the 0 form is ck if f is. Okay, this is also called differential 0 form. For a one form, we define a differential one form to be a map, which I'm going to call omega from u to Rn star. Exactly like the derivative df, the total derivative or total differential or whatever it's called, exactly modeled on df, we are now defining a one form to be nothing but a map omega from u to Rn star. At each point A, it gives you a linear functional from Rn to R. Now that just means that we can write omega at the point x of v to be nothing but some a1x dx1 plus anx dxn, where a1 an are functions from u to Rn. So as you can anticipate, we say omega is a ck differential one form if a1 an are ck on u, or ck smooth. That just saying ck on u doesn't sound nice. Or ck smooth on u. So this is the definition of a differential one form. A differential one form is modeled on the total derivative or total differential df. At each point on the open set, it assigns a linear functional from Rn to R. So the best way to view this is view Rn as the tangent space at the point of the open set U. So it is essentially, the differential one form is essentially a linear functional on the tangent space at each point of U. This viewing the differential form as actually being on the tangent space is going to become very, very crucial once we define differential forms on manifolds in maybe 7 or 8 more videos. We will do that. Okay. Now, what are the examples of differential forms? Well, again, example, the most important example is the total derivative or total differential. Total derivative or differential of a function. This is the most common example of a function. So this is the most common example of a differential form. So the next question that you should be asking is, given a differential one form on U, is it going to be the derivative of some function from U to R? And given a one form, how do I find out what that function is with df equal to omega? We will address this in the next video. This is a course on real analysis, and you have just watched the video on differential one forms.